This section of the book concentrates on ways you can separate the variables to solve for a differential equation. And really, it's just an exercise in integration. So it's not really anything that's extremely new or really a part of the BC curriculum. I mean, it's really about separating the differential expressions here and then integrating, which you've done a fair amount in AB already. So if we just take a look at this, acknowledging that this expression here is really the differential expression dy dx, then we can just go ahead and separate the variables. So these kind of fall into the category of the separable differential equations. And so we're going to multiply each side by 3y. And we're going to then have this expression of 3y dy over dx equals the square root of x. And then we're going to go ahead and re-express the differential expression dx over here on the right-hand side by a process that is, very similar to multiplying both sides by dx, although it's not exactly that, but we can kind of think of it in that nature. Once we've separated the variables, then we can go ahead and go through our integration process. So really what we're doing is we're integrating y dy, and we're integrating x to the half power dx. So integrating y gets us 1/2 y squared. Integrating x to the half power gets us 2/3 x to the 3/2 power. And since we did perform an integration, or technically an anti-differentiation step, we do need a constant of integration, which we can just tack on to the side of the expression that has x. We don't have to put them on both sides, since constants of integrations can always be combined anyway. And so going ahead then and solving for y, we've got 3/2y squared equals 2/3 x to the 3/2 plus c. So we're going to go ahead and multiply by the reciprocal here. Cancel this out. So we end up with y squared equals, now this is kind of interesting because technically we've got to multiply this whole side by 2/3, but 2/3 times c is still a constant, so we're just going to still continue to call this c. Some people will actually get really picky about this and maybe call this c1 and this c2, since it's really 2/3 times c1. It's not really that important though. The only time that becomes important is if we have to find a particular value, a particular solution, where we need to start to put initial conditions in and actually find values for c1 and c2. So I'm just going to call it c2, and then we're going to multiply through here and get 4/9 x to the 3/2 power. So there is our solution to the differential equation. In this example, we're going to use a slope field to graph two approximate solutions to the differential equation dy dx equals x times y. And one we want to have go through 0, 1/2. And so I have used an online applet to show that approximate solution that goes through 0, 1/2. So here is 0, 1/2, and if you notice the purple solution here is just like we mentioned before, kind of following the contour of that of those tangent lines at each point, and the applet I'm using is called Calculus Applets, and it's calculusapplets.com. It's actually a very useful site. And so I have the differential expression here, x times y. I put in my particular solution, which is right there, and so I get that approximate curve. And so if I wanted to go through maybe a solution of let's keep that at 0. Let's go to -2 here. I guess it doesn't let me do negative numbers. Oh, there we go. Let's see if we want to go through a solution of -2 here. You can see that as we get closer to -2, that's close enough, it follows those contours down there. So this whole family of solutions that has x value of 0 and a y value varying from -4 to +4, you can see how those whole families of solutions look similar. They just get kind of flatter as you get towards the x-axis, and then they get narrower as you get away from the x-axis. And if we would change this to maybe like 3 and go through that same sort of range, I fixed the solution at x equals 3, and so that's kind of fixing the width to a good extent of that of those particular solutions. So those are solutions fixed at 3. And if we would go with 0, 0, and we can vary the y. We can also vary the x's. So you can see in varying the x values, we're kind of adjusting that width. And if we vary the y values, we're kind of sliding along that y-axis, so we're varying not only the width but kind of that start location, that vertex, so to speak. So if we would then graph another solution, like I said, let's, instead of graphing 0, 1/2, maybe we graphed 0, -1.5. So we would have something that looks kind of like that. That's a really bad approximation. Let's try that again. There we go. So 0, -1.5, and we try to make those transitions as smooth as we can. So something to that effect. I also want to integrate this so we can find a particular solution. And so we're going to go ahead and separate those differential expressions. So we have dy dx equals x times y. So we're going to divide each side by y. And so we have dy over y equals x dx. And integrating both sides, this is the natural log of the absolute value of y, and this is 1/2 x squared plus c. So looking at this, looking at the initial conditions here, we want to go through, we want this purple solution here, we want to go through 0, 1/2. So we have the natural log of 1/2, that's the value for y, equals 1/2 times 0 squared plus c. So our constant of integration is the natural log of 1/2. So our particular solution looks like the natural log of the absolute value of y equals 1/2 x squared plus the natural log of 1/2. Here's another example to solve for the particular solution of a differential expression with this initial condition. When x is 0, y equals 10. So again, we're going to go ahead and separate the variables. So we have dy equals -3/4 times the square root of t dt. And we're going to integrate both sides. And so we have y equals minus 3/4 times the integral of t to the half dt. And integrating t to the half gets us 2/3 t to the 3/2 and plus c. And so looking at the multiplying two fractions here and simplifying, it looks like we have -1/2 t to the 3/2 plus c. There's our general solution, and to find the particular solution, we're looking at this initial condition. So when y equals 0, excuse me, I said that wrong. When t equals 0, y equals 10. So y equals 10 when t equals 0. That makes the math a lot more simple. And so we're looking for a constant of integration here of 10. And so the particular solution looks like y equals, coming back up here to the general solution, minus 1/2 t to the 3/2 and plus 10. In this example, it's more of a word problem. It has us putting together the relationship between the rate of change of n and n, which would be a differential expression, and that gets us into kind of a growth and decay sort of model, which we'll be hitting in the next section. So it's kind of almost a little preview. So it says write the differential equation and evaluate the solution. The rate of change of n. So if we look at what that means, rate of change of n, that means the derivative of n with respect to time. That's typically what we measure rates in. So we're talking about a dn dt. The rate of change of n is proportional to n. So if you remember back from Algebra 2, we use proportionality constant k. So when we're talking about proportional to n, we're talking about a constant times n. And then it gives us some initial conditions here. When t equals 0, n is 250. When t equals 1, n is 400. And it says, what is the value of n when t equals 4? So what we're doing is we've got a couple of initial conditions here. We've got this initial condition and we've got that initial condition. And the reason why we need two initial conditions is because we need to not only find the constant of integration, but we also have to find the proportionality constant k. And so if we go ahead then and take this differential expression and come up with a general solution to it, we're looking at dn, looking at dividing each side by n. So we have dn over n, excuse me, equals k dt, and you might recognize this as an exponential function. And so we have the natural log of the absolute value of n equals the integral of k dt. So that's what we get when we integrate both sides. And so we're looking at the natural log of the absolute value of n equaling kt plus a constant of integration. And so in order to get a function in terms of n, we're going to have to use our exponential rules here, and that is raise each of these both to the exponent e, and then we have n equals e to the kt plus the constant of integration. And if you know your rules of exponents real well, you know that if we have a sum up in the exponent, we can write that as e to the kt times e to the c. And if c is a constant, then Euler's number, which is roughly about 2.7, to that constant is still a constant. So I'm just going to kind of backtrack here, and I'm going to put a subscript 1 with all of those constants, and I'm going to call this then, where we take Euler's number and raise it to a constant, I'm just going to call that the constant c. Let me write that a little more clearly. There we go, the constant c. So what I have then is n is basically c e to the kt. Okay, so there's our relationship between there's our, excuse me, I said that wrong. There's our general expression for that differential equation. And so now we have to deal with the initial conditions. So we have initial conditions of t equal to 0 and n is equal to 250. So we have that initial condition. And we have an initial condition of t equal to 1 and n is equal to 400. So we have those two initial conditions, and we want to know what happens at a t of 4. So we're going to use these two situations so that we can find c and k. So we're going to go ahead and set up those two situations. So at 250, we're going to set up this expression. So when n equals 250, t equals 0, this is basically e to the 0, and we know e to the 0 is 1. So we know our constant of integration here is 250. Okay, and then now that we know that, we can set up ourselves for this condition, and that is we have an n of 400. We know we have a constant of integration, or what we would call an initial condition of 250. That might be our initial value at time t equals 0. If we're talking about a growth or decay problem, and time of 1. So now we can use this to find k. And so we're going to divide each side by 250. And 400 divided by 250 equals e to the k. And we can go ahead and take the natural log of both sides. So the natural log of 400 divided by 250 equals the natural log of e to the k, which is just k. So our constant of integration is the natural log of 400 over 250. If we reduce that, let's see, that's 40 over 25, and we can further reduce that. So that's the natural log of 8 over 5. So there's our constant, there's our value for k. And so our particular solution then looks like if we had a general equation of c to the kt, our particular equation then looks like 250 e to the natural log of 8 over 5 times t.